You might be questioning the applicability, the usefulness of this odd-even mode analysis. I made an argument that symmetric circuits occur frequently in electrical engineering, but you might question whether we would then attach to those symmetric circuits sources that are likewise symmetric, either even or odd. Why would we take a two-port device and attach on both of the ports a source, and not only a source, but a source that had precisely the same magnitude and phase, or magnitude and opposite phase? It seems like a very limited applicability of this idea of odd and even mode circuits. But it turns out that odd-even mode extends beyond sources that are symmetric when we apply superposition. And of course, to do this, we need to have circuits that are linear independent. Likewise, I should have written here, they need to be reciprocal, and the reciprocity is difficult to mess up with most of the simple elements that we are dealing with in microwave engineering, but that is also one of the considerations. So if all that is true, if it's linear and independent reciprocal devices, we can go through and apply the idea of superposition to the circuit, and find that odd-even mode circuits will likewise come in handy. To demonstrate this, let's do an example. Let's go back to our original circuit that we had, that a single plane of bilateral symmetry, and we separated the 50 ohm resistor into two 100 ohm resistors in parallel. We separated the 200 ohm resistor into two 100 ohm resistors in series. We're going to label this as port 1 and label this now as port 2, and we are going to try to determine the admittance matrix for this two-port device. And we know how to determine the admittance matrix. We need to go through and put a voltage on port 1, for example, and a short circuit on port 2, and then determine the currents at port 2 and port 1, and then likewise the opposite for putting a voltage at port 2. So let's go through and see if we can do that. All right, so to determine our first two conductance parameters, we want to go through, and transadmittance parameters, I should say, we want to go through and we put a non-zero voltage source on port 1, and we put a short circuit on port 2, and then determine the current so we can determine I2. Now, mathematically or symbolically, we're going to represent a short circuit as a zero-valued voltage source, and that's what it is. The equation V is equal to 0, that describes a zero-valued voltage source, is likewise the circuit equation for a short circuit. The voltage difference from one terminal to the other across the short circuit must be equal to 0. And so we have a source on either port of this device. On one side, it's a non-zero value VG. On the other side, it is precisely a zero value voltage. Now, this is an asymmetric set of sources, as you'll ever see, of course. VG cannot be equal to 0, so they're not equal to each other. Certainly, they're not equal but opposite. They're not same magnitude and 100 degrees out of phase. What we've done by putting a source, non-zero source VG here, and a zero source at this point, a short circuit, is we've destroyed the symmetry associated with the circuit. And from this, we no longer have a virtual open nor a virtual short along this plane of bilateral symmetry. In fact, there is no plane of bilateral symmetry anymore once we've connected these very asymmetric sources. Turns out, though, we don't have to give up on our even and odd mode circuit analysis. We're going to apply a little trick, and this is quite a gem. This is a very important aspect of this analysis, and it's very important that you understand where this comes from and why it works. So we're going to go to our source at port 1, VG, and we're going to rewrite it as two sources in series with each other, each one having a voltage which is 1/2 of the original VG. And of course, we could go through and do KVL here and find that the voltage from this terminal to this is equal to the sum of VG over 2 plus VG over 2, which of course is VG, the original source. So this is equivalent in every way to this. We can, in our schematic, replace this with these two sources without changing the circuit at all. Now we can do a similar thing to the source on the other side of our circuit, our short circuit, which is a voltage source of a value of 0. We are going to rewrite that 0 valued voltage source again as a sum of two voltage sources. In this case, one voltage source with a value of Vg over 2 and the other one with the value of V minus Vg over 2. In other words, the same magnitude, but 180 degrees out of phase, either j pi or minus 1. But if we go through and add these two voltages together, we do KVL across, we find the voltage between these two terminals must be equal to 0, which is exactly the same as we'd have with our original source. So these two things are equivalent. We're going to replace this voltage source in our circuit, this short circuit, now with two voltage sources in series. And so you might think this is the world's most complex short circuit. We take a voltage source, an ideal voltage source with the value of Vg over 2, and then put it in series with another voltage source that has the opposite value of minus Vg over 2, so that their sum is 0. So why do we go through all this difficulty to make simply a short circuit into, again, what seems to be the world's most complicated short circuit? So now this is our circuit that we have, and again what we're trying to do is determine the transmittance parameters here. We have a voltage source on this end with the value of Vg, which we split into two pieces. We have a short circuit on this end, a voltage of 0, which we've split into two equal but opposite pieces. And again, you look at this and you're thinking we're just making the circuit more complex, and we haven't done anything to reestablish symmetry. These sets of voltage sources are different than these sets. They are not related directly in terms of even mode or odd mode symmetry. But what we can do now is apply superposition. And in superposition, remember, we can go through and turn off each source or some combination of sources and do an analysis, and then turn on the remaining and turn back off the original and do a second analysis and add the two together. We can determine the answer via superposition. And that's why we split these things up, because now we're going to apply superposition to do our analysis. The first thing we're going to do is turn off two sources, one on the left side and one on the right side. We're going to turn off this bottom source, and by turn off we say we set it equal to 0. Its voltage now becomes 0, it becomes a short circuit. Likewise, this voltage source, we're going to set it equal to 0. We're going to turn it off, and that becomes a short circuit. What we have left then in that case is simply a voltage source Vg over 2 on one side and Vg over 2 on the other. Exactly the same source, both in magnitude and in phase. Hopefully now you see why we went to all the trouble of splitting our sources up into two pieces. We turn off this bottom source and this bottom source, and what we have left is Vg over 2 on one side, Vg over 2 on the other. We have reestablished the symmetry of our circuit. We now have an even mode symmetry, equal sources both in magnitude and phase on either side of the circuit. Again, these two things are 0, so they don't disrupt the symmetry either. We can think of them as, of course, short circuits. And so now our plane of bilateral symmetry has turned into a virtual open. Now we have two half circuits that we can analyze and get the answer. And so we go through and we determine for one half circuit all the voltages and currents. So we call this the even mode analysis, and it gives us the even mode currents and even mode voltages. Since we're looking for the transmittance parameters, what we're trying to determine here is simply the current that is going into each of the two ports, I1 and I2. Now this isn't the current, it is the even mode current that we have calculated here. And it's very simple to do. Since we have open circuits and 0 current flowing here, this current can be determined from Ohm's law. It's simply this voltage source, Vg over 2, and remember, don't forget the 2, divided by 200. And so it becomes Vg, I put Vs here, but that really should be Vg, divided by 400. That is equal to this current. But we also need to find the current on port 2, and that's very simple. Because we have even mode analysis, the current on port 2 is exactly the same as the current on port 1. And so by this analysis we found both the even mode current for I1 and the even mode current for I2. That was just one half of our superposition process. To complete the superposition, we need to go and turn off our original sources, and by turn off a voltage source, we set the value of voltage equal to 0, make it into a short circuit. We go back and turn on the first two sources that we turned off, restoring them to their original value. In this case, the bottom one was Vg over 2, but recall for the other side, that bottom source was a minus Vg over 2. And so what we have here on one side is a source of Vg over 2, and a source on this side has a value of minus Vg over 2. Now we've created an odd mode symmetry. This voltage source in this voltage source have the same magnitude, but they are oscillating 180 degrees out of phase with respect to each other. Because the remaining circuit has bilateral symmetry, this plane of bilateral symmetry now becomes a virtual short or a virtual ground. And we know the voltage across it is going to be equal to 0. So now we analyze the resulting half circuit. We can take this virtual short here, we can split it in half and have a half circuit to do the analysis. Again, we look at the circuit and see that it's become very simple. Ultimately, what we care about is this current here. This resistor has been shorted out. The voltage across it's 0, so there's no current flowing through here. This current will divide and go through these two resistors. But these two resistors now are in parallel. If you look around the circuit, they're in parallel, so we can combine them into one 50 ohm resistor and then use the Ohm's law to define this current. Vg2 divided by 50 is going to be equal to this current I10. So we also need to find the current on port 2, but it is easily determined. Because we're doing an odd mode analysis, the current at port 2 now is simply the opposite of the current that we found at port 1. And so the current at port 2 is going to be a minus Vg, or in this case I put Vs, I'm confusing S and G there, I apologize for that, the source voltage divided by minus Vg divided by 100 would be the value of the I2 odd current. All right, so again, we get one answer and we can immediately determine the other answer by multiplying the first one by a minus 1. What do we do now? What do we now do with this even mode solution and the odd mode solution? What did we do with the even and odd current for each port? What we ultimately want to do is determine, of course, the total current I1 and I2 there. So how do we determine that from the even and odd mode analysis? Well, remember, ultimately the even odd mode analysis is a process of superposition. We took 4 sources, we determined one solution for the first 2 sources and the other solution for the second 2 sources, and therefore the solution for all 4 sources is simply the sum of each of those 2 solutions. That's the beauty of superposition when applied to a linear circuit. So for example, we can say what is the voltage at port 1? We simply add our 2 voltage sources together, the one for even mode and one for odd mode, and of course that gives us Vg, which was our original voltage source. Likewise, for the voltage at port 2, once again we add the 2 voltage sources together, apply the superposition of those 2 solutions, and V2 is equal to 0, which is what we needed it to be because we are putting a short circuit on that second port, on port 2, to get the correct answer for our trans admittance parameters. More importantly, what we want to do is then determine the current at port 1 and the current at port 2 by simply adding the even and odd mode solutions together. And so we go through for current at port 1 and add the even mode current at port 1 to the odd mode current at port 1. And that is the correct answer. That is the current that we get for port 1. For port 2, we go through and do the same thing. We add the even mode current at port 2 and the odd mode current at port 2. Now be careful here. Remember, the even mode current at port 2 is equal to the even mode current at port 1. But the odd mode current at port 2 is equal to the opposite of the odd mode current at port 1. So I2E plus I2 odd is equal to I1 even minus I1 odd. I1 is the sum of the two even and odd mode currents that we got for the left-hand half circuit, and I2 is the difference between the even and odd mode we got for each of the solutions for the left half circuit. So be careful right here. Sometimes students will mess this up. If you come up with an I1 and I2 that are the same, you've probably done something wrong. Not always. Sometimes the odd mode current can be equal to 0, and so you do get the same answer. But if the odd mode current's not equal to 0, then you should get different answers, or will get different answers, and so use that as a sanity check. So our final results here, when we add our even mode current to our odd mode current, add these two values together, we get VG over 80. If we go for the second current over here, again, we add the even and odd mode current for the second port, I2, and notice the odd mode current for the second current is equal but opposite the odd mode for current 1 there. So we get a plus sign there, and we get a minus sign there. That's the only difference between the two, are the plus and minus. And so we get this result, I2 being different than I1. And so that's our solution for the current I1 and I2 when we have a non-zero voltage source of VG at port 1 and we have a short circuit, a voltage source of 0 at port 2. And that is the circuit that we needed to analyze to determine the transadmittance parameters. So let's complete the problem here. Let's determine the transadmittance parameters. In this case, let's do y11 and y21. And again, we know that that's by definition the current I1 when the voltage at port 2 is equal to 0 divided by the voltage at port 1, and that turns out to be 1 over 80. Likewise, the admittance parameter y21 is equal to the current at port 2 when the voltage at port 2 is equal to 0. Take that current divided by the voltage at port 1, and that gives us our transadmittance parameter. And notice that in both cases, this is a value independent of VG, as it must be. Again, if you still have the source voltage in your answer, then you don't have an answer at all. So here are two parameters, y11 and y21. This is half of our admittance matrix. But it turns out we're done with the admittance matrix because by symmetry of the device, again, because this bilateral symmetry, what we label as port 1 and what we label as port 2 is sort of arbitrary. If we go through and put a source at port 1 and a short at port 2, if we flip it around, that would be the same thing as doing the second part of this problem to determine y22 and y21. I'm sorry, y12 rather. And so from symmetry of the device, and we'll talk about this later, we know if we know y1, we also know y22. Likewise, if we know y12, or y21 rather, then we can determine y12, the transadmittance parameters. So in this case, when you have bilateral symmetry, and again, we'll talk about this later in the course, you have a situation where your admittance matrix is greatly simplified. You only have two independent parameters, and once you find those two, you can fill in the rest of the matrix. This is true likewise for any two-port device that has bilateral symmetry, whether we're talking about admittance matrix or impedance matrix would be the same thing. And later on, we'll find that's true for a scattering matrix as well. So, putting the pieces together, this is our full admittance matrix for this two-port device, and I sort of facetiously say it wasn't that easy, and certainly it was from the standpoint that if we were to go over here and change even one of these values, let's say change this 100 ohm resistor to 200 ohms and leave this 100, then we've destroyed the symmetry of our circuit, and finding the admittance matrix for that circuit would be exceedingly difficult. We couldn't apply any of the symmetry ideas that we just got through talking about. We couldn't split our circuit into two half pieces. We'd have to go through and analyze the complete circuit with KVLs and KCLs to go through and find the answers. Moreover, once we found y11 and y21, we'd have to go through and put the source on the other side and move the short back here and redo the analysis because at least y22 would not be equal to y11 in that case. So the fact that this is symmetric really has saved us a lot of time and a lot of effort. The key thing here is you have to understand, though, what is an even odd mode mode analysis of going through and generating your even and odd mode sources, of determining the even mode and odd mode currents, and then adding them together properly to get the final answer. And so if you have that tool in your toolbox, if you understand this process, again, it'll make solving problems like this relatively easy. And without them, we're talking hours and hours worth of effort, and almost certainly somewhere in there you'll make a mistake.